How's everybody doing today? I hope well, and I hope you've had your coffee. Me, I like mochas and macchiatos. Today, we're probably going to be talking more about mochas than macchiatos. Why do I like coffee? Because I like the caffeine. I like the stimulant. Caffeine is made up of atoms that are covalently bonded to each other. Covalent as opposed to ionic. In a covalent bond, the electrons are being shared between the atoms in the bond. When it's ionically bonded, it means that the electrons are either pulled or pushed towards one atom or another in the bonding. The molecular formula of caffeine is pretty complex. 8 carbons, C8, 10 hydrogens, H10, 4 nitrogens, N4, and 2 oxygens, O2. Now that doesn't tell you a whole lot about caffeine. It doesn't tell you what the molecule looks like, and it doesn't tell you its properties. A better way to think about the molecule is to draw a picture. And here you see a two-dimensional representation of caffeine. Now, this two-dimensional representation assumes that you understand that the molecule is actually three-dimensional. And so there are limitations on this two-dimensional picture. In fact, there's pretty severe limitations because structure determines function. Structure determines properties. And if you have an incomplete representation of the structure, you really can't infer very many properties. So what we do is we move from that two-dimensional representation to a three-dimensional model, a structural model. Now this ball and spoke model is the way that we can depict the three-dimensional structure of molecules. This particular molecule is formaldehyde. 2 hydrogens, which are the white balls, 1 carbon, which is the black ball, and 1 oxygen, which is the red. Now, we see single bonds, or at least one spoke between the hydrogens and the carbon. But we see 2 spokes between the carbon and the oxygen. That's a double bond. In a structural model, you can look at the shape as well as the bonding and the three-dimensional structure. So let's move back from this simple molecule back to caffeine. You're looking at the chemical structure or chemical formula of caffeine and the picture depicted on your screen. All of the atoms in caffeine are covalently bonded. Now, the structure, this three-dimensional structure, tells the chemist not just what is bonded together, but how it's bonded together. And similar to formaldehyde, we see different types of bonds. We see some double bonds on the oxygen, we see some single bonds on the carbon, and we see 2 ring structures. One is a 5-membered ring, and the other is a 6-membered ring. Now this is a limitation of these structural models. In this 5-membered ring, there are some double bonds, but I wasn't able to put those spokes in place. Similarly, in the 6-membered ring, there's some double bonds. I didn't put those in place. But what you do see pretty clearly are each ball is a different atom. The white are hydrogen, the blue are nitrogen, the black are carbon, and the red are oxygen. And so you can see where each atom is located in the three-dimensional structure of caffeine. So that's caffeine. And we mentioned that caffeine is a covalently bonded molecule by making a very small change to caffeine. And so this molecule, which is theobromine, looks a lot like caffeine. The difference between these 2 models is very subtle. There's only a change of the group that's hanging off of this nitrogen. One has a methyl, and one just has a hydrogen. A small difference in structure can lead to a pretty significant difference in properties. In this case, it's the difference between the flavor of coffee and the flavor of chocolate. But it could also be the way that the molecule interacts with energy and light, or spectroscopy. It could be the way that the molecule reacts with other things, reactivity. And it could be the speed that the molecule reacts, kinetics. Each of these properties, and many more, are tied to the structure of the molecule.